Hi. In today's lecture, I'd like to talk to you about the potential energy for systems with conservative forces. So we're going to be deriving some of the potential energy functions and discussing some of the details of potential energy in this lecture. So first of all, what is potential energy? Okay, we've talked about kinetic energy and we've talked about work, okay? So potential energy is the energy that's a result of the configuration and the location of the particles within a system. So if you can imagine a system with interacting particles, like for example the planets in the solar system orbiting the sun, or a system of point charges like located relatively near one another, then they're interacting via these, forces that are relatively long range. So, for example, we talked about universal gravitational force, Newton's law of universal gravitation, and we talked about the Coulomb force, for example. Now, the magnitude and direction of these forces is dependent upon the position and the configuration of those planets or those charges. And the direction of the force could change. For example, if you change the location of one planet with respect to another, it'll change. And if you increase the distance, then the force will also decrease, all right? So you can see that the position and the configuration of the particles in the system greatly influences, right, what the force is. Now, that also translates into an energy, as we'll see. So there's an energy related to the system that's based upon how those elements of the system are positioned and configured with respect to one another. And that is the potential energy. And the potential energy will change as the position and configuration of the particles within the system changes. The potential energy function will also depend upon the type of force that governs the interactions. So for example, you'll have a different potential energy function for the Coulomb force than you will for universal gravitation. And you'll have a different potential energy for them for springs, okay, if they're connected by springs. Now, before we get into the derivations, there's a couple of points that I want to really go over and make sure that you understand. And that's the idea of a conservative force versus a non-conservative force. Okay, so what do we mean by this? Well, first of all, we've already covered energy conservation. And we understand that that means that energy can't be created or destroyed. And so what that means is that if the energy of a system changes, then that means that energy was transferred into or out of the system via some force, via some mechanism of energy transfer. Now, some types of forces, and we'll call them conservative forces, they keep the energy within the system and they don't transfer energy out of the system. Non-conservative forces, however, can transfer energy out of a system. And oftentimes they do this by converting the system's initial energy into heat, or internal energy, which we'll talk more about later. And then that heat can be radiated away or conducted out of the system, all right? And it'll leave the system, and then the system loses energy, okay? You can also transfer energy into the system, as we've seen, by pushing on it, okay, and giving energy in that way. So if you have a conservative force, though, and that means that that force keeps the energy within the system, then there's a few hallmarks and details about these forces that allow you to recognize them. And one is that a conservative force, when it does work, it doesn't depend on the path taken. So for example, if I'm lifting an object like this pen, then the amount of work done by gravity doesn't change whether I lift the pen straight up or over to the side and up or on a diagonal line. As long as the initial and final heights with respect to the ground are the same, then the work done by gravity will be the same because gravity is conservative force. Now also it means that if I start this pen in one position, move it through some change, and then bring it back to the same position, that for that total cycle, that total round of motion, that gravity has done a net zero work, right? It did a certain amount of work on the pen going up, but then that same amount of work in the negative was done doing down, and so, the net sums to zero. So that's a closed path. If you have a closed path, then the work done by a conservative force on that closed path, the net work, is zero. So that's one of the hallmarks of conservative forces as opposed to non-conservative forces. Now, there's several examples of conservative forces, and some of them will derive the potential energy function for today. So, for example, the Coulomb force is a conservative force. That's the attractive or repulsive force between two charges. Gravity here on Earth is a conservative force, but also Newton's universal law of gravitation, okay, really it's the same force, so it shouldn't be surprising that that is also a conservative force. And then finally, the spring force is also a conservative force, okay? Now, there's a lot of non-conservative forces, but here's a few. Friction and drag, that's everybody's favorite. Everybody can remember that friction and drag transfer energy out of the system, right? But there's also others like tension. Tension is a non-conservative force. And then pushes and pulls that, for example, if I push on a desk or, something to move it, then that's non-conservative, all right? Okay, so now that we've laid that foundation, let's explore exactly what function is going to enable us to derive the potential energy for different systems. So we associate the potential energy for a system with the work done by a conservative force that's acting between the members of the system. So if you have a conservative force, you can derive the potential energy by finding the work done by that conservative force. And then the work done by that conservative force will be the negative change in the potential energy of the system. All right? So, in general, W sub C is equal to minus the change in U. So, if you can find the work from a conservative force, then the negative of that will be the change in the potential energy. So, let's do the easiest example first. Let's do gravity here on Earth, okay? Now, in a previous lecture, we derived the work kinetic energy theorem, and we defined the work for a force as being the integral of the force dotted with the displacement, okay? So F dot dr, as is shown here in this top equation. And now we can go a step further and say that that work is equal to the negative change in the potential energy. So, for example, if I'm translating some object from location A to location B, then the work done in that translation by this force would be W sub BA, and that would give us the negative change of the potential as it moves from BA, and then that would be the integral from location A to location B of F dot dr. Now, let's just do Cartesian coordinates first. So dr would be dx I hat plus dy j hat plus dz k hat. In other words, you're taking a little tiny step in each one of the three directions, x, y, z, which is associated with the unit vector I hat, j hat, and k hat. An alternative way of writing that unit vector notation would be the triangular brackets here. And so you can see that this is a vector with x, y, and z components, dx, dy, dz. Now, we've also got location A and location B in vector notation here. Here's their position vectors. I'm going to call the coordinates of location A, x sub A, y sub A, and z sub A. And B, similarly, x sub B, y sub B, z sub B. Okay? Now, the force of gravity here on planet Earth is mg, where g is the acceleration due to gravity, which is 9.8 meters per second squared down. Now, your textbook uses the y direction to indicate up and down generally. So if we were to write that force in unit vector notation, it would be minus mg j hat, where g is just a constant 9.8 meters per second squared, m is the mass, and j hat is the unit vector associated with the y direction, and then the minus sign indicates down. Okay. Now, this is a constant force. G is 9.8 meters per second squared, and the mass is constant. We're assuming no change in mass. And so that means that we can write the definition for the work here. W sub BA would be the force dotted with dr. But since the force is constant, I can pull that out of the integral, okay? So then I have minus mg j hat dotted with the integral of dr, okay? Which would be I hat dx, I hat integral dx, j hat integral dy, and k hat integral dz from the limits from location A to location B for each one of those three directions, as is shown here in this equation. Now, taking that over to this next slide, we realize that if you do the dot product between j hat and I hat, or j hat and k hat, then since those unit vectors are perpendicular to one another, they give you a dot product of 0, okay? And the only one that survives is the j hat term, because j hat dot j hat is 1. So then the integral for y, the y direction, is the only one that gives you a non-zero value. And since j hat dot j hat is 1, that means that we can write the value of the work from b to a as minus mg times the integral from ya to yb of dy. And that gives me minus mg times yb minus ya, because the integral of dy is just y. And then we evaluate that over the limits of integration here. Now this value for the work would be equal to the negative change in the potential energy. So that means that if we were to write the potential energy change from B to A, then we would just drop that negative sign, and we'd have the change of potential energy from B to A would be mg times yb minus ya. Now a delta of the potential energy would be, that would mean any delta is final minus initial. Our final position is location B, and our initial position is location A. So delta U would be UB minus UA. So what that means is that the potential energy for location B would be mgyb, and the potential energy for location A would be mgya. Now generally in most introductory textbooks, what they do is they just say that this change in the y position is the change in height, which they often indicate with an h, and then they say that the change in the potential energy is mgh. So that brings up an important point about potential energy that I'd like to discuss in a little bit more detail, and that's the idea of reference points. Really, it's the change in the potential energy during some interaction or process that's of interest, and not the raw value. And the reason that the raw value of the potential, say the potential at location B or the potential at location A, the reason that that's not too important in and of itself is that if you change your origin, right, then the value of yb or ya will change. I mean, really, it could even be negative. Like, let's say that you put your origin up here and your particles are down here, then you can have a negative potential energy, a gravitational potential energy, and that would not really mean much, right? But even if you translate your origin, say, up and down in the y direction, your change in the potential energy during a process would be the same, right? That would be the same change in the potential energy. So that's why we say that changes in potential energy are more important and more meaningful than the raw value of the potential energy. Because if you change your origin, you've changed everything, right? Okay, mechanical energy. This often gets cited in introductory physics textbooks. And the total mechanical energy of the object is equal to the kinetic plus the potential energy. Now remember, we went over the kinetic energy in a previous lecture. The kinetic energy is 1/2 mv squared, 1/2 the mass times the speed squared, okay? And now what I'm telling you is that the mechanical energy is the sum of the kinetic plus the potential. Now when you work energy conservation problems, which is what's coming up next, oftentimes you're using the idea that if you have only conservative forces, that the total mechanical energy of the system as a whole does not change. And that if there's a change in speed, it just comes from some change in the potential energy, right? So for example, if you gain speed, then you've lost potential energy, and the sum of the kinetic plus the potential stays the same. That's true for conservative forces. For non-conservative forces, it's a different story, but we'll talk more about that later, okay? So let's derive this equation for the mechanical energy as applied to, say, this gravitational potential energy equation. And we can do that by using the work kinetic energy theorem that we previously developed, okay? So we know that the work done by a force in moving it from location A to location B, so that is symbolized here by W sub BA, that work is equal to the change in the kinetic energy. We derived that relationship in a previous lecture. So the change in the kinetic energy from B to A, delta K BA, is equal to 1/2 mvb squared minus 1/2 mva squared, assuming B is the final location and A is the initial location. Now, we already derived for the gravitational potential energy, gravitational force, that the work done from B to A would be minus mg times yb minus ya, and that would equal to the change in the potential, the negative change in the potential energy, delta UBA, negative delta UBA. Okay, so If we take the middle part of this equation right here, okay, and we rearrange the stuff, putting everything to do with A on one side, here the right, and everything to do with B on the left-hand side, then you can see that we get 1/2 mvb squared plus mgyb is equal to 1/2 mva squared plus mgya. Now, given our definition, then the mechanical energy is the kinetic plus potential, then that's saying that the initial mechanical energy, EA, is equal to the final mechanical energy, EB. And that would be true if there's only conservative forces acting on the system, and these are the conservative forces in question, the gravity here on Earth. Okay, so that's how we get that, and we can do that derivation, that simple derivation, for any conservative forces. All right, let's move on and talk about another type of conservative force and derive that potential energy function. And so this one is the work done by a spring. So that situation is shown here in this image on the left, courtesy of Thompson Higher Education. So here we have a horizontal spring on a frictionless surface, right? A perfect horizontal spring on a frictionless surface. Physicists love ideal scenarios, right? So remember that Hooke's law says that for this little 1D problem, that the force is equal to the negative spring constant, K, times the displacement of the mass from its equilibrium position. So the equilibrium position here, it would be the unstretched length of the spring. And what we've done in this problem is chosen our origin such that that's where the mass sits when it's at its unstretched length. And that's shown here in image B. Okay, so our origin is right there where the orange block is in image B. And then any displacement from equilibrium would be the x-coordinate, okay? So that's how that's written. Now, we're just going to do this for 1D, okay? So here, the force is equal to minus kx, all right? And so if the block undergoes some displacement from equilibrium to some initial to some final position, and I'll call the initial position x sub I and the final position x sub f, then the work done by that spring on the block would be the integral from the initial to the final position of the force, which is minus kx dx, right? That would be the integral of minus kx dx. Now, this is a very simple function to integrate. So k is a constant. You can pull that out of the integral. So you'd end up with 1/2 negative 1/2 kx squared, which you would then evaluate from the initial to the final point. So that would give you negative 1/2 k times x final squared minus x initial squared. And if you wanted to, you could move that negative sign, multiplying it through, and you would have 1/2 kx initial squared minus 1/2 kx final squared. And that would be the work done by the spring on the block. Okay? Now we've solved for the work. Remember that the work is equal to the negative change in the potential energy. So if the work is 1/2 k x initial squared minus x final squared, then the change in the potential energy would be 1/2 k times x final squared minus x initial squared. All right, so that would be the change in the potential energy from the final to the initial position, right? And the delta U would be equal to U final minus U initial. So that means that the final potential energy would be 1/2 kx final squared, and the initial potential energy would be 1/2 k x initial squared. So that means that for an arbitrary point x displaced from equilibrium, the potential energy associated with this system is 1/2 kx squared. Now, we talked about reference points before. Remember that for this equation, we've chosen the reference point as being the origin at the unstretched length of the spring. So if you put that point as your origin, then your potential energy is 1/2 kx squared. If you chose some other random point, you'd get a constant offset, which would kind of mess you up a little bit, okay? Okay, we did gravity here on Earth. Let's do Newton's law of universal gravitation and derive the potential energy for that function. So here I've got a little image of a satellite or something orbiting Earth, okay, in some distance away from planet Earth. And it moves from some initial location, R initial, to some final location, R final, okay? Now, remember that Newton's law of universal gravitation, the force associated with that, says that F is equal to minus g big M little m over r squared r hat. Here, g is the universal gravitational constant, which is 6.673 times 10 to the minus 11 in SI units. Big M is one mass. Remember that the force is attractive between all masses, so I called one of the masses big M and one of the masses little m, okay? And that's the mass in kilograms. R is the center of mass to center of mass distance in between the two objects, okay? And it's an inverse square law force, so the force is proportional in magnitude to 1 over r squared here. And then r hat is the unit vector, which connects the center of mass of one object to the center of mass of the other. Gravity is always an attractive force that points along the center to center in towards the other mass. And that's shown here in this image. Here we're just showing the force of the satellite, force on the satellite by planet Earth, and it points towards the center of planet Earth. Now, if you move the satellite along this red path here, which is some arbitrary path, and it changes the center to center distance, right? So it changes r, and it also changes the angle theta with respect to it, okay? Let's assume for now that we're in some plane, okay? We're in some plane looking down. A lot of orbits are like that, quite frankly. You could lay it out and it's kind of an ellipse or a circle in one 2D plane, okay? So that's not too crazy to do that. So then if you were to move along some arbitrary path in that plane, then the change in your displacement, so that would be d of delta r, which is your displacement vector from the initial to the final point, that would be changing the radius in some amount, so that would be dr r hat plus, now you can also change the angle, so the component which describes that in polar coordinates is r d theta theta hat, okay? Theta hat points along the path as the angle changes. So if it's a circle, for example, dr points along the radial direction, and theta hat would point along the angular change of direction as you move around the circle, okay? So that's going to be our little differential vector. We're going to use polar coordinates here, not Cartesian, because it's more convenient for gravitational potential energy. Okay, so we're going to start again with our equation for relating work, potential energy, and the force. In general, for conservative forces, we say that the work, if you're moving from A to B, W sub BA would be the negative change of the potential energy, delta U, negative delta U BA. And that would be the integral from position A to position B of F dot the displacement, here D delta R hat, or D delta R. Now our D delta R in polar coordinates would be dr r hat plus rd theta theta hat. Written in a two-dimensional vector notation this way, it would be dr comma rd theta, okay? Now, we're going to say that position A is at some distance, center to center distance r sub A and some angle theta A, and position B is at rb and theta B, similarly. And we're going to plug this equation for the force that we discussed on the previous slide into this equation. Now, unlike the gravity here on Earth, the force is not constant anymore. It's going to vary with the position, and so you can't have that out front. You have to move it inside the integral because r will change. So then we have here r hat, right? So the force, though, is in the r hat direction. So we can put that out front for our dot product. We would have r hat dot, r hat times the integral of RA to RB minus G big M little m over r squared dr, right? And then we would have the force, which would be minus G big M little m over r squared r hat dotted with the theta hat component, which would be the integral then of theta hat times the integral of theta A to theta B of minus, G M little big M little m over r squared r d theta, okay? So what I'm doing is I'm doing the dot product of this force with each one of these little d delta r's in turn, okay? And that means that my minus G big M little m over r squared has to move inside the integral for both, okay? However, just like before, we've got to think about what the direction component there is for our dot product. So r hat dot r hat, that's 1, right? But r hat dot theta hat is 0 because r hat and theta hat are perpendicular to one another. R hat points radially and theta hat points tangent to any circle, right? So those will always be perpendicular. So that means that this second term in the integral, r hat dot theta hat, goes to 0. So this second integral with respect to theta, it doesn't count, okay? Because that r hat dot theta hat component makes it go away, okay? So we're just left with the r hat dot r hat integral. And so that means that the work from b to a is equal to the integral of ra to rb of minus g big M little m over r squared dr. You can perform that integral. The g big M little m, those are constants, so you can pull that out front, and then you're just doing the integral of 1 over r squared dr. Okay. Now that's r to the negative 2 dr. So to find that integral, you increase the power by 1. You have r to the minus 1, and then that makes a negative sign here out front. So then it ends up being g big M little m over r evaluated from ra to rb. So that gives you g big M little m times 1 over rb minus 1 over ra, and that's equal to the negative change in the potential energy, negative delta UVA. So we can set this here, minus g big M little m 1 over rb minus 1 over ra equal to UV minus UA. And that means that the potential energy at location B would be minus g big M little m over rb, right? So what that means is that you can write your potential energy function, U, as minus g big M little m over r for some arbitrary point r, right? Now, this means that the reference point would be infinity, okay? So as r goes to infinity, then you have, basically a constant, negative constant over infinity. And dividing by infinity, as that approaches infinity, it goes to 0. So unlike the other functions that we had here, where the reference point was the origin of the coordinate system, the 0 point of the potential energy was at the origin, like for springs, and for gravity here on Earth if you choose your coordinate system wisely. Here instead, right, you have a reference point of infinity as to where your potential energy goes to 0. Now let's discuss that for just a second. Oftentimes for certain problems like springs and gravity here on Earth, we choose our coordinate system wisely, right? And for springs, that means putting the origin at the equilibrium point of the spring. And that means that your potential energy is 0 at this point, right? But it also means that your force is 0 at that point. So when your force goes to 0, when the force on that mass is at its equilibrium point, well, the force is equal to negative k times the displacement from equilibrium. So if the spring is sitting at its equilibrium point, at that point, the force is 0. And the potential energy is 0 too, okay? Same thing for gravity here on Earth. If I make my reference the floor or the table or something where something's going to stop falling, and then I drop it, right? Then once it reaches the table, it can't fall any further. So the net force on the object at that point would be 0. And so we choose our reference point at that location, okay? Now, if you do not make a wise choice, then you will have a net force on the object, even though it's at the origin. But we're talking about wise choices here. Okay? But for inverse square laws, things are different. In those cases, the force is only 0 when, for example, the particles are infinitely far apart. Okay? And so the force goes to 0 as the distance in between the particles gets really, really large. And so the potential energy will also be 0 at those points. So the reference point for Coulomb force, which is an inverse square law force, and the universal law of gravitation, that reference point where U is equal to 0 is chosen infinitely far away. Okay, I've been talking a lot about the Coulomb force. I'm not going to derive it in this lecture. And the reason is I usually assign that one for homework. But the deal is that the derivation is super similar for these two potentials because they're both inverse square law forces. So you have, in general, some constants, right, times 1 over r squared, and it's a radial force. So the derivation should be pretty much the same for both of these forces. So I want you to do that one for homework. When you do, though, you're going to end up with a potential energy that's shown here, okay? For the Coulomb force, the potential energy associated with that is 1 over 4 pi epsilon naught times the magnitude of the two charges, or the two charges, Q1 times Q2, divided by the center-to-center distance between those charges r. So you should end up with that for your potential when you're doing Coulomb law derivation. All right? Okay, I hope that made sense. I hope you somewhat enjoy it, and I'll see you in class as always.